Governments, investors, and consumers are heavily pressuring major corporations to cut their greenhouse gas emissions. The math is simple. To slow climate change, the biggest emitters have to drastically scale back. To track this, policymakers use a metric called carbon intensity. This is calculated by taking a company's total emissions and dividing it by their total revenue. It tells us exactly how much pollution a business generates for every dollar it earns. But there is a massive gap in the system. Thousands of public companies simply do not report their environmental data. The disclosures we do get are often incomplete, inconsistent, or entirely voluntary, leaving huge holes in the global ledger. If we cannot accurately measure a company's footprint, the entire mechanism for holding them accountable breaks down. Investors cannot penalize the heavy polluters, and markets cannot reward the businesses actually investing in green operations. When direct emissions data is missing, analysts try to fill in the blanks. They look at basic, available traits, like how old a company is, its total assets, or its profit margins, and try to estimate the carbon footprint from the outside in. For decades, the standard mathematical tool for these estimates has been linear regression. It tries to draw straight, proportional lines between a company's financial stats and its environmental output. The problem is that modern corporate operations do not move in straight lines. The relationship between a company's debt, its board structure, and its supply chain emissions is complex. A simple straight line completely misses the chaotic clusters of real-world variables. Relying on linear math to predict carbon emissions is like trying to navigate a sprawling three-dimensional maze using a one-dimensional map. It lacks the structural depth to capture reality. To solve this, researchers turn to machine learning. Instead of forcing data into rigid equations, these algorithms are designed to map the actual, non-linear complexity of a modern corporation. They tested 6 different mathematical models, and one consistently outperformed the rest, an advanced ensemble method known as XGBoost. Instead of drawing a single line, XGBoost builds a massive sequence of overlapping decision trees. It learns incrementally. If one tree makes a mistake, the next tree in the sequence specifically targets and corrects that error, allowing the algorithm to map those chaotic data clusters. Researchers stress-tested this algorithm against thousands of U.S. firms across an 8-year period. They intentionally split the data to see how the model handled the stable pre-COVID economy versus the volatile, disrupted post-COVID years. The linear models performed poorly, registering near zero accuracy. XGBoost dominated across every time period, demonstrating that predicting emissions requires highly adaptive algorithms capable of tracking shifting corporate behaviors. But the researchers wanted to test a much harder scenario. What happens to the model's accuracy if we completely delete all historical carbon data? They simulated the exact blind spot investors face every day. By hiding the past emissions records, they forced the algorithm to try and predict a company's carbon intensity using only its financial, operational, and structural data. The algorithm didn't break. Stripped of its primary environmental indicators, XGBoost shifted its weight to a completely different set of corporate characteristics to maintain its predictive accuracy. These 3 charts show exactly what the algorithm prioritized when the carbon data was removed. The massive bar leading every single graph represents corporate governance. It became the most powerful predictor of a company's carbon footprint in the absence of direct reporting. Across the pre-COVID years, the post-COVID years, and the combined timeline, the math remains consistent. The data shows a strong predictive link between a company's physical environmental footprint and the specific organizational structure overseeing it. Governance is a broad category, so we have to look deeper into the algorithm's decision-making process to see exactly which factors matter most. This granular breakdown reveals board characteristics, like independence, expertise, and sustainability committees, do the heavy lifting. This makes sense. Expert boards allocate capital to manage climate risk. Secondarily, the algorithm leans on profitability, liquidity, and firm value, factors dictating cash for green investments. If you want to know how much carbon a company is likely pumping into the atmosphere, look directly at who is sitting at the head of the boardroom table. The accuracy is striking. Using only these governance and financial proxies, this machine learning model can explain up to 88% of the variation in corporate carbon intensity. For investors, this provides a reliable way to systematically screen and rank climate risk across portfolios, evaluating even those companies that do not publish their emissions. For corporate executives, the message is clear. Withholding environmental data no longer shields the company from scrutiny. The algorithm. To dive deeper into the research, explore the predictive models, and learn more about how governance shapes our climate future, visit sherryshu.com. Machine learning has closed the reporting loophole. With external models accurately estimating emissions from a distance, the ability to keep environmental performance private has vanished.